Hello Internet, my name is Quinn and this is Blondihacks. I'm working on my locomotive this week, continuing with the lubrication system. We built the oil pump last week and today we're going to make the little clockwork mechanism that drives that pump at a 40:1 reduction ratio off of the main drive axle. It's a really cool little mechanism. It's a lot of fun to make. Some very exciting parts in this one, so let's go. I'm going to have to start on the drawing board with this one. I know, but if you don't understand what I'm building, then none of the work that you're about to see is going to make any sense at all. So here's the basic mechanism. It's a ratchet with two leaf spring pawls on it. This leaf spring here is the stop, and this one down here is the advance. This mechanism is solving two very important problems. First, it's gearing down effectively the pump 40:1 from the main drive axle. Obviously, the locomotive's wheels can be spinning quite quickly, but the amount of oil needed by the cylinders is actually tiny, like a drop every 10 to 15 seconds, something like that is plenty. So this mechanism needs to have a very large reduction on it, and importantly, while the locomotive moves in both directions, this pump can only ever be turned forward. A ratchet wheel like this very cleverly and compactly solves both problems. The effect of a ratchet is that it only captures motion in the desired direction. This is driven by an eccentric strap off of the drive axle, and regardless of whether that axle is turning clockwise or counterclockwise, the drive linkage is oscillating back and forth, and the ratchet ensures that only the forward motion of that is ever captured. So the only noticeable effect of the locomotive going forward or backwards is the phase at which that motion is captured. So technically, if you started this whole mechanism in the same place and rolled the locomotive forward or backward from there a fixed distance, the pump would be 90 degrees out of phase in both situations. But of course, the phase of this pump doesn't matter. Then of course, the ratchet itself moves one tooth per full cycle of the rest of the mechanism, which means that it again creates a 40:1 gear reduction. Now the motion isn't continuous, that's the trade-off with a ratchet, but it doesn't need to be for this pump. That 40:1 reduction is also why we want to make sure the pump only ever turns in one direction, because the locomotive, being a switcher, is going to be shuttling back and forth all the time, changing direction lots, and the pump would effectively lose progress because it's only moving a little bit for a given amount of road travel distance. And if you're shuffling back and forth, that pump piston might shuffle up and down a little bit, but never actually complete a full cycle. So we want to make sure that all travel of the locomotive accumulates progress on the pump towards the next drip of oil. Sorry, that was a lot of talking. Let's make some chips and see if we can make this thing actually work. That ratchet needs to be sturdy, obviously. It takes a lot of abuse, so it's going to be made out of tool steel and it's going to be hardened. I have this very nice piece of maybe tool steel. As regular viewers know, I moved my shop a couple of years ago, and unfortunately, while I do keep all of my stock sorted and labeled, if you've ever moved a machine shop a few thousand kilometers across an international border, then you know that things happen and some of the stock got mixed up, and I don't know for sure if this is tool steel or stainless. So what I'm going to do is cut a chunk of it off, and I'm going to test it by attempting to harden it. While some stainlesses are heat treatable, I know for a fact that all of the ones that I've bought in this particular ground bar are not. So if this is heat treatable, then it is tool steel. I'll do a test first of all with the unhardened piece using my PTC Instruments hardness tester. It uses a calibrated spring punch, and then there's a microscope with a scale printed inside it that tells you based on the size of the punch, the larger the punch, the softer the material. So this is registering 35 Rockwell C, as you would expect. Now, every time I show this tool, people always look up the price and their hearts sink. Yes, it is a very expensive tool. This was donated to the channel by the fine folks at PTC Instruments. It's way overkill for a hobbyist. I would not own it if they hadn't given it to me. They were very kind to do that. It's actually very reasonably priced on the scale of industrial hardness testers, but like I said, overkill for a hobbyist. If you are a hobbyist who wants some form of hardness testing, just get some hardness testing files. They work just fine. I'm going to start by heating this up to cherry red, and then I'm going to dunk it in vegetable oil because it smells like French fries. Then I can clean that up a bit and redo the hardness check. I don't need to bother tempering it or anything. I just need to know if it can be heat treated, and then I know for sure this is O1 tool steel, which is the only possible material that it could be other than stainless, based on knowing what I've bought in the past. And sure enough, that is now showing a blistering 65 Rockwell C. It's actually the limit of what this can measure, this instrument, so it may be harder than that. Suffice it to say, it's harder than a coffin nail, so this is definitely tool steel. Good deal. An easy little secondary check you can do is to just try to run a normal file over it. And in this case, that file is like, whoa, human, go home, you're drunk. I can't even begin to touch that. Then you know for sure it's hard. I can now label that bar for next time, and thusly I've slowly been unwinding the damage that was done when some of my materials got mixed together in the move. All right, you're going to force me to talk about this. I heard all your caps lock keys go down in the comments. Why don't I use a magnet to check for my stainlesses? All right, here we go. I'm going to have to explain this because this is one of those things people who pride themselves on knowing things think they know, but isn't actually very useful in the real world. In general, yes, many stainlesses are non-magnetic. However, lots of stainlesses are magnetic, and the ones that are officially not magnetic are also sort of magnetic. So what most people often know is the difference between austenitic and martenitic stainlesses. The former are non-magnetic and the latter are magnetic. However, in a machine shop, the 300 series, for example, that you're often going to encounter are in fact paramagnetic. What that means is, in the presence of a strong magnetic field in some materials, localized magnetic dipole moments can be created by the spin of unpaired electrons. So in fact, a strong magnet such as this neodymium one will actually stick to it just fine, even though this is austenitic stainless. Now, it's not a very good connection, and you can kind of tell from how strong the magnet is sticking to it whether it's probably still stainless or not. But the point is, the magnet test is actually pretty inconclusive, and I don't recommend using it. I acknowledge you are all very smart. Now let's move on and I'll make this part. I'm going to start with this piece of round bar, and I'm going to turn more than you would think I would need. I'm actually going to turn a fairly long section of this, even though the ratchet wheel is quite thin, and that's because I need a work-holding stem or mandrel, if you like. The defining challenge of this wheel is, of course, the teeth, and I'm going to be doing that on the shaper. And if you've been watching this channel regularly, you know I recently built a rotary indexing fixture for my shaper, and the work-holding solution on that fixture requires a mandrel, a stem on the back of the part to hang on to. So the outer portion of this is going to be the ratchet wheel itself, so I've turned it to the outer diameter of that. And then behind that, I'm going to use a grooving tool to turn the mandrel diameter for the indexing fixture. I'm going to go one step further right behind where the ratchet wheel will be. I'm going to turn it down a little further to create a runout area for the shaper tool that will allow it to break the chip. And the finish on that mandrel is pretty terrible because that grooving tool did not like tool steel, but that's fine. The finish is irrelevant in this case. There's my little runout groove. And then I'm also going to bring in a turning tool, and I'm going to use the compound to turn a taper between the back of the finished part and that runout area. That's going to give support for the back surface of the part, because this is going to be a form tool cutting operation with the shaper in tool steel. So all of that adds up to high tool pressure. And I want to make sure that this setup is going to be as rigid as possible. That little scribe line there is the finished width, give or take, of the final part. It's a little bit generous, and then I'll turn a taper on the back of this with the compound. So that'll give kind of a sloping runout area for the shaper tool, and then it's going to end up in that smaller diameter that is smaller than the minor diameter of the tooth, which is then going to break the chip. While I'm here, I'll do the drilled and reamed bore in the center of this ratchet wheel. It's going to go over the axle, the drive axle, for the pump. This actually just gets Loctited in place on there. There's no key or set screw or anything to hold it in place. Given the nature of this part being hardened and how small it is, Loctite just seems like as good a solution as any. It's what the drawings recommend, and I see no reason to deviate from that. That's it for the lathe work. It's time to get this thing over to the shaper and see if we can make some real noise. I'll Yahtzee this thing off. Before I can set up the shaper, I need to understand the geometry of the teeth on this ratchet wheel. The drawing gives an overall dimension, but doesn't give any detail about the geometry itself. However, we can work it out intuitively. We know that the angle of the tooth has to be more than 90 degrees, or the pawl can't catch on it. However, straight 90 degrees is probably not enough because it's a round surface, so it has to be more than 90, but it can't be too much more than 90, or else the end of the tooth gets fragile and it may not be able to settle into the bottom of that hook, as it were. So somewhere in this range between these two is what we need. Obviously, this basic surface flattening tool that I have on my shaper all the time is not going to be correct for this job. I dug through my tool bits, and one of these lathe tools I have has quite a sharp point on it. It's a little bit sharper than a threading tool, and I thought this might actually be pretty good if I can kind of hold it at the right angle. So I'm going to try that out. Let's get the tool holder out of there. This is a 3/8 tool bit, so I made a packer block on the shaper, of course, to make it easy for me to put 3/8 tool bits directly into the lantern tool post. This tool post is designed for holding a tool holder, and the clamping bolt on it is not long enough to get a tool bit all the way down in the bottom by itself. The other reason to use this packer block is it allows me to get a lot of stick down on the tool, which I'm going to need for my rotary fixture setup. So the block is going to support that tool all the way down the back, and I can stick it down way out of the tool post without losing too much rigidity. All right, here comes the exciting part. Get the vise out of there, get my shiny new indexing fixture in here, and let's put this thing to work for realsies. I have done one test part on this in brass, and that is the extent of it. So I have no idea, honestly, if this thing is going to work. So I'll get that dialed in square to the shaper. Pretty easy to do. Now I have lots of plans for this rotary fixture, but I knew the first thing I was going to make with it was this ratchet wheel. However, I didn't actually check if I have a 40 division wheel in the set of plates that came with my rotary table. Yeah, classic me. I don't actually have a 40 division wheel. I have this one here that has a bunch of odd numbers on it. It's got 39 and 41 on it, which might seem strange, but remember these indexing plates or these dividing plates are designed to work with the rotary table, which has a worm drive in it that has either a 60 or a 90-to-1 reduction in it. So you don't need so many divisions because you're doing the multiples and factors of that 90-to-1 and the reduction on the indexing plates with the sector arms. Because I'm using these plates for pure indexing and not dividing, I'm stuck with whatever the raw number of divisions are on the plates. So I decided to go for the 39 because in principle that's going to produce a little bit more oiling than 40 would. Figured a little more oil is better than a little less, and it should be close enough. I'm oversimplifying a bit there because in principle the stroke of the eccentric driving this mechanism has been matched to the circumferential distance between two teeth on the ratchet wheel, and they're technically supposed to match. However, there's some wiggle room there, and 39 is again close enough. I made a test part in brass to get the tooth geometry sorted out because the angle and depth of the cut is going to determine the final geometry, and I had no idea what was going to work. So I did a whole bunch of little patches of different profiles until I found one that worked well. And once that was set, then I brought in the actual tool steel part and got it set up to do the cut for real. Pretty exciting stuff. So really the only remaining unknown variable is whether this tool steel is going to be too difficult to cut with this fixture and this setup, because of course the brass is easy. I'm going to blue that up so that I can see what the cutter is doing. That's especially helpful on these kinds of rotary setups. And then I do one cycle by hand with the ram to make sure my clearances are all okay. You know, that clamping bolt's awfully close to the indexing plate there, but hey, in machining, clearance is clearance. Clarence, don't call me Shirley. That seemed to cut just fine, so here we go. One stroke, and rotate, do another stroke. And I wasn't sure if I was going to be able to do each tooth cut in a single pass or if I was going to have to do multiples, but honestly, full depth of cut, 14 thousandths with this form tool seems to be just fine. I'm not seeing any signs of rigidity being too low. Everything's working just fine. I ended up doing 2 strokes per tooth just as kind of a spring cut, just in case something was deflecting, but honestly, I don't think it was necessary. I never saw anything happen on the spring cuts, but just in case, it didn't take long to do 2 strokes for each tooth. Moment of truth for a rotary setup. The final tooth. Does it land directly between the first and last? Oh, look at that. Perfect. This is where that bluing really helps because you can make sure the spacing of each tooth is correct, and thus it will land correctly at the end. Honestly, that seemed to go incredibly well. I really have no notes on that. It's hard to show on camera because of how small these teeth are, but hopefully you can kind of make out the little sawtooth shape that came from that operation. The rotary fixture performed flawlessly. Really, really happy with that. The only real issue I had was because this is tool steel and it's form cutting, there was some pretty nasty burrs on the teeth. The teeth look kind of messy, and it's just because there's burrs on the ends of them and such. I didn't want to get too carried away with deburring because at this stage the teeth are really fragile. So if I start going at them with a file or a Kratex block or something, the teeth are going to get dinged or bent or removed even. I ran a razor blade between each pair of teeth to scrape out any burrs that are between them, and then the ones on the outside of the teeth, I figure they're going to wear off in normal use anyway, and I'm just not going to worry about it. So now I can go back over to the lathe and part it off, which made a heck of a racket while cutting through the teeth. You can see with a test piece of spring steel how it seems like it's going to lock nicely into those teeth. I did this same test with the brass before deciding on my final tool profile, incidentally. That's how I knew they were going to work. And now, finally, we can heat treat it because there's no more machining needed on this part. Dunk that in oil, and of course now it's really hard, so that I clean up the surface so that we can see the color, and then I use the torch to temper that to a straw yellow. With parts this small, it's easy to temper them too far, so I just feather the torch in there very lightly and give it a chance for the color to develop before I go back in. And as soon as I see that straw yellow, I dunk it in water to arrest the heat soak, otherwise it will temper too far. I'll zip through a few parts in the mechanism here that aren't very interesting. There's a brass dogleg arm that drives the ratchet wheel from the eccentric strap. There's also a little mounting block for one of the springs, and there's a little pin that connects these things together, a bunch of screws that had to be shortened, you know, the usual little miscellanea that aren't worth filming. I do want to talk about these leaf springs, however, because they are interesting. This is spring steel, which can be challenging to work with in the hobby shop. This is 10 thousandths thick, as specified in the drawings, which incidentally came from this box of assorted shim stock. You can buy these online. It's not very expensive, and this pack is a lifetime supply of all different sizes. Really useful stuff for making tools and fixtures, all kinds of things. But of course, spring steel is hardened, so it's essentially unmachinable. I mean, there are ways you can do it, but for the hobbyist, consider them unmachinable. So after laying out the dimensions, I'm going to cut them close to my layout lines with aviation snips. Aviation snips, if you're unaware, are color-coded. They come in red, green, and yellow versions, depending on whether you're cutting left, right, or straight cuts. I'm using the green-handled ones, indicated by the stripe. Sorry, the Milwaukee branding is confusing there, but these are the green or right-handed ones, and they can cut straight or right-hand curves. That direction also tells you which side of the cutters will be distorted by the cut, and that's important, so I can keep that on the off-cut side of my part. The main downside to using the snips is that they leave little tooth marks on the edge of the part, which we don't want, so I remove those over on the bench grinder. The trick to doing this is you have to hold the part vertically. If you hold it horizontally, the stone will grab it and distort it. It'll bend it over the pliers and wreck it. Also, while doing this vertically, do not let the top corner of that part touch the wheel, otherwise it will dig in and the wheel will grab it and destroy it. So do it carefully, and also do it very gently because we don't want to put any heat into the part. It's very easy to overheat a part this small on a grinding wheel, and of course if you overheat it, then you'll take the spring temper out of it, and then it's no longer spring steel, it's just steel, I guess. Then my final step is to use a hand stone to get right up to my layout lines, and now I can start measuring with a micrometer, make sure that my sides are parallel and I'm hitting my dimension. You can also use the piece flat on the stone to deburr it. For me at least, I've landed on this 3-step process because this has allowed me to make very small spring steel parts that are right on dimension to the thousandth and have nice edges on them, but your mileage may vary. The final step is to put 2 holes in them, and drilling spring steel can also be tricky if you don't know a couple of tricks that I've learned from Stefan Gottsventer and Mark Presling over the years. You can drill spring steel with high-speed steel, but you got to run the drill very slowly, in this case about 350 RPM, which is about an order of magnitude too slow for a drill this small, and you put a piece of cloth in between the drill and the material, and that keeps the drill from grabbing the material as it breaks through. With those 2 tricks combined, you get really nice, clean, round holes and no distortion on the part at all, and very low drama. It works surprisingly well. Drilling spring steel can be very difficult, but those 2 tricks make it super easy. So thanks, gents. Well, in principle now, we have all the parts needed to fully assemble this ratcheting drive system for this oil pump. It's a lot of little parts. I've watched enough YouTube to know this is the part where I'm supposed to snap my fingers and it all gets assembled. That didn't seem to work. Maybe both fingers? Nope. Maybe I'm just a really bad YouTuber. Alright, I guess I'll actually just show you how it goes together. The Scotch yoke and crank you saw me assemble before, the axle threads into that. Again, there's a right-hand thread on that, and since the pump only turns forward, it won't ever unthread itself. Then there's a little mounting block for the stop spring that goes on the top of the ratchet wheel. The ratchet wheel itself goes over the drive axle, and that will get Loctited in place once I verify the final position of it. Make sure to put that on the correct direction. That would be a fatal mistake. Then the little drive spring goes on the lever arm. And the stop spring goes on top of that little block. Well, for a first assembly, it looks really cool. However, on closer inspection, there are some issues to sort out. The first is that stop spring is being bent up at a bit too much of an angle. I'm pretty sure I know why this happened. If you watched the video where I made this oil tank, you know I had a math error on all of my vertical dimensions because I didn't account for the thickness of the bottom plate of the tank. And so I think most things, including these mounting holes, are a little bit too low. And so that's an easy fix. And then the other issue that's a little more puzzling is that the drive spring doesn't actually reach from where it's mounted on the arm to the ratchet wheel. And on that one, I triple checked every single dimension in all of the related parts, and I could not find a single error anywhere. I don't like to say there's an error in the drawings because that's almost never the case. It's basically always my fault somehow, and I would put money on that every time. But in this case, honestly, I couldn't find the error. Anyway, easy fix. I just made that spring a little longer. And for the stop spring, I remade that mounting block just a scooch taller so that it's less severely bent. And that looks like that is now working extremely well. Look at that. That's an extremely satisfying ratchet motion, I gotta say. Here, listen to it. That arm is driven by an eccentric strap off of the drive axle. As I said, I went ahead and made that off camera. It's identical to the one that I made for the water pump. You don't need to see me make the same thing again, just slightly different dimensions. So we'll get that installed on there, a little E-clip, and that all seems like it's right. Everything's moving nicely. Let's get it installed on the locomotive and see if it actually works. It's pretty tricky to fit in here. There's just barely enough room to get the screwdriver in there, but it is doable. Then I got to align the eccentric, of course, make sure that that connecting rod is running nice and square. Get that tightened down, and then get that strap all assembled. Get a little oil on there, a bit of assembly lube. Let's do a hand chooch and see if that's working. Oh yeah, that looks good. It's moving 1 tooth per cycle. Occasionally it goes 2 teeth, which is either a slight imperfection in my manufacture, or as I said earlier, perhaps because there's actually 39 teeth on that wheel instead of 40, but either way, occasionally going 2 teeth is harmless, just means it'll oil a little extra. If it was missing teeth, that would be concerning because the pump would be stalling, but I ran this a lot and never saw it miss a tooth, so that seems encouraging. Now for the real test, let's chooch on air, see what happens. Look at it go. That is so cool. Look at that. You can see the pump kind of moving in slow motion up and down as the ratchet goes. That's really neat. And that Scotch yoke is walking laterally a little bit, as I said earlier in one of the earlier videos. I may still put a shim behind that crank, but I don't think it's necessary. I ran this for a long time on air, and I didn't see any problems caused by that little bit of walking in the yoke, so I think I'm probably going to leave it alone. I gotta say, though, this seems to be working flawlessly. Looking underneath, you can see every few seconds another drip of oil comes out of that pump, and it really seems to be working nicely. Here's a look at that unidirectional feature that we talked about at the top of the show. Running the locomotive backwards by hand, you can see that the ratchet wheel still moves in the same direction that it was in the previous footage. Pretty cool. Just to demonstrate that, I'll run it forward now again, and you see the ratchet wheel always runs in the same direction no matter what. It's a really neat device, really clever mechanism. I love watching this thing go. I guess all that's left is to put the lid back on and call it a day. I got a nice fit on that lid, so it's pretty satisfying to slide that in there, clicks in place, won't go anywhere. Well, there's the final pump and tank assembly. I really am thrilled with this assembly. You know, I had my dramas making that tank, and it's obviously a bit of a black sheep of the assembly here, but the whole thing works and nothing leaks. And you know, this was a pretty tricky assembly to make in many respects, especially that ratchet wheel. I've never made anything like that before, so I had no idea how that was going to go, and I'm very pleased to see a positive result. So thank you so much for watching, and thanks to my patrons for making all this happen, and we'll see you next time.